So we proceed to your hyperbolic functions, integrals of hyperbolic functions. Okay, as you can see in the figure, or I mean in the slide, so we have 10 formulas, the same as your integrals of your trigonometric functions. So for this one is, I think what is familiar from your derivatives is formulas 1, 2, and then 7, 8, 9, 10. 7, 8, 9, 10. Because I think these are the more familiar um, derivatives from your calculus 1. So I think also they are just a counterpart of your trigonometric functions, but they only differ in the operation or the sign. So for example, in your trigonometric function, the integral of a sine is negative cosine, but in your hyperbolic function, the integral of your hyperbolic sine is positive cosine, hyperbolic cosine. But so I think that's what differs in the in your trigonometric and in your hyperbolic functions. So notice also in our integral of hyperbolic secant, hyperbolic tangent. So instead of having a positive value of your hyperbolic secant, so we have a negative value here. But in your trig functions, the answer for this one is positive, right? So I think this one is the difference only. Because for cotangent and cosecant pair up, we still have a negative value as the answer, the same as your trigonometric functions. So for formulas 3 to 6, so notice that we have 3 ln answers, ln, ln. So I think the other format for your second answer is also ln, but this is one answer also in terms of hyperbolic, I mean inverse hyperbolic tangent. So you just have to, mm, oh, there's h here. There's h here, yeah, h. So there's h here. Okay. Okay, so for the ln formula, so I think you can just um, derive this one or answer it manually, just like what we did in our trigonometric integrals. So for tangent, hyperbolic tangent is you get the components of tangent. So you have hyperbolic sine, hyperbolic cosine, and then you use the u sub technique. So u sub technique, and then what happens is you reach an integral of du all over u. That's why the answer is ln u plus c. Okay. So you don't have to memorize the formulas for 3 to 6. So you can just manipulate it using your basic u sub technique. Okay. So also the last transcendental function is your exponential function. So in your derivative, the derivative of e to the power of u is equal to eu du. So notice that they are just the reverse of the other. But in integrals, we just have a plus c because again we don't know if the given equation has an extra constant. So of course, despite getting the derivative on the right side, so derivative of a constant is 0. So vice versa. So we also have another exponential function. So we have your a as your base. So also take note that your u variable is a function of x. Okay, and then a is a constant. Okay, so in the second formula, your a parameter here is a constant. So raised to a function of x. So it may be 3 to the power of x, 3 to the power of x squared. So the particular answer for this one is a to the power of u all over ln of a. So if you want to verify if this one is correct, so you can derive this answer. So again, I think in your derivatives, this one is called the quotient rule. I don't know if oops, wrong spelling. Ano, quotient. Oh, so, basta mo na siya. So quotient. Okay, so I think if you recall your derivative, so we have v du minus u dv all over v squared. All right. So for you to appreciate your hyperbolic and your exponential functions, so we'll be solving 6 equations. Okay, so let's start with the first example. So we have hyperbolic sine x, hyperbolic cosine squared x with respect to x. So again, you may use the basic approach. So you can use u sub. So again, according to the u sub, you always choose the complicated term, and the higher the degree, so it's more complicated. So this one is linear, this one is quadratic or second degree. So automatically this one becomes our u parameter. So u is equal to hyperbolic cosine x. So getting the derivative is we have du is equal to, so derivative of sine hyperbolic cosine is positive hyperbolic sine x dx. So notice we have sine here, sine, then we have dx. So it simplifies into u squared du. Okay, so automatically this becomes u cubed over 3 plus c. So final answer is hyperbolic cosine, or as what I tell my class para dili siya, so that you can easily read the function. So you just incorporate h. So cos cube x all over 3 plus c. Okay, so this is the final answer. So again, you can read it in an informal manner. So instead of hyperbolic cosine, and it takes a longer time to read it in that manner or in that way. So instead of saying hyperbolic cosine, so you can say cos. Then instead of hyperbolic sine, so you may call it as cosine, tangent, cotangent, secant, cosecant. So at least it's easier to pronounce. But again, that's just the informal way of reading the hyperbolic functions. So the proper way is you say hyperbolic first, then the corresponding trigonometric function. So hyperbolic sine, hyperbolic cosine. Okay, so I think you don't have any questions for number 1 because it's just a basic concept of u sub. So let's proceed to the next one. Okay, so next is we have tangent squared x dx, hyperbolic tangent squared x dx. So how do we answer this one? So if you look at the formula, we don't have any integral for hyperbolic tangent squared x. But we have a formula for hyperbolic secant. So secant squared x is equal to tangent x plus c, right? But we don't have any squared. So for us to be able to answer this one is we will be approaching our hyperbolic identities. So another set of identities that needs to be reviewed. So I don't think if this one was introduced in your senior high or in your high school, but you still need the hyperbolic identities. Okay, so your hyperbolic identities from your tangent is um, 1 minus tangent. So just try to search your hyperbolic identities. So this one is one of the three Pythagorean hyperbolic identities. So you also have the other two, which is your 1 minus cotangent, then cosecant squared x. Then this one is sine squared x minus cosine squared x is equal to 1. So just try to research them online. So this equation, so applying the hyperbolic identity, so this becomes 1 minus secant squared x, hyperbolic secant x dx. So notice that we can derive now because your secant squared x is a formula. So we have x minus tangent, h na noon ako noon, tangent. Okay, so x minus hyperbolic tangent x plus c. So this is the answer. So if you notice that to be able to answer this one, so we only have two lines, but if you don't know your hyperbolic identities, so you cannot answer the equation given above. Okay, so questions? So I think you just need to review your hyperbolic identities. Okay, so we go to the third example. So this one is an exponential function. So looking at your equation, so we have the integral of 3 raised to x squared minus 4 times x dx. So again, if we look at your exponential integrals, so this one is in the format of a to the power of u du. So the answer for this particular integral is a raised to u ln of a plus c. So the same as your inverse trigonometric functions. So we declare or we identify your a parameter, your u parameter, and then your du parameter. So we make it in a manner that your equation looks like the given format. Okay, so a is equal to 3, and then your u parameter is x squared minus 4. So this one is already okay. This one is okay. So for your du, so getting du is we have 2x minus 0 dx. Okay. So notice that this one is 3. That's your a. your x squared minus 4, that's your u. So your x dx, notice that you have also an x dx on your du, but we have a 2 as a coefficient. So we still need to divide by 2. So du over 2 is equal to x dx. So this term here is equivalent to this one. So notice that every term in your equation can be replaced. So there's nothing left in the equation. So we have a raised to u, then du all over 2. So taking 1/2 outside the equation, so that's a to the power of u du. So getting the answer, so again, don't forget to multiply 1/2. So 1/2 times a to the power of u all over ln a plus c. So bringing back the value of your a and u parameters, so that's 3 raised to x squared minus 4 all over ln 3 plus c. So combining 1/2 with the answer, so 3 raised to x squared minus 4 all over ln 2 ln 3 plus c. Okay, so notice that your denominator can further be simplified, but I'll be accepting this answer. So your answer may be, so again in logarithmic functions, so the coefficient of the log function is the exponent of the base. Baka na siya, the exponent. So this may be represented as ln 3 squared plus c, and then this becomes 3x squared minus 4 all over ln of 9 plus c. So you can also have this answer. Okay, so questions? Okay, so no question. So let's proceed to the fourth example. So the same as the previous example, so we still need to follow the a raised to u du because we have an exponential function. So looking at your equation, so you have the integral of a raised to tangent t all over cosine squared t dt. So looking at your equation, so you have first a exponential function in the numerator. Then we have a trigonometric function in the denominator. So you might be confused on how you approach this problem, but my suggestion is you approach first the exponential function because it's more complicated compared with your trig function. And then usually if you try your u sub, so most likely it will eliminate the extra term in the equation. So of course, if so, as what I've told you always, that your integrals are a trial and error method. So if it cannot be approached by a basic concept, so we have an extra advanced technique that I will be discussing in sa March. Okay, so that's why what I gone siya. So you need a lot of practice for you to be able to determine what particular process you're going to use. Okay, so here is we have, so again, we declare our A, U, and du parameters. A, U, and du parameters. So your a is still a. Then your u parameter is tangent t, the exponent of your a parameter. So next is we determine your du. So derivative of tangent t is secant squared t dt. Okay. So notice that we have dt all over cosine squared t. Now your secant can be expressed as 1 all over cosine. So this one may be represented as dt all over cosine squared t. So notice that this term here is the one in your derivative of u. Okay, so in the given equation, so there's nothing left to be substituted. So everything can be replaced. So we have a raised to u du. Then the answer is a raised to tangent t all over ln of a plus c. So this one is your final answer. Okay. So question so far? Okay, so I think there's no question. So again, um, what I have told you so far are just the basic concepts. So again, if you cannot solve the basic concept, so there are advanced techniques or processes that I will introduce on March 3. So what I will give you in your problem set can be solved by the basic approach, U sub, other sub techniques, by the identities. So no advanced process yet or advanced techniques. Okay, so here is we have an exponential function again. So this one is in the format of e raised to u du. So again, the answer for this one is eu plus c. Okay. So before we answer this one, so we try to eliminate first the constant 6. So we have e raised to 1 over x all over x squared dx. So again, we declare or we identify your e, your u parameter, and your du parameter. So your e is still e because that's the equation. Then your u parameter is 1 over x. And then du parameter, so derivative of 1 over x. So for you not to be able to be confused, so let's try to convert this one into its exponential form. So that's x raised to negative 1. So derivative of this one is negative 1 times x raised to negative 2 dx. So we have negative x raised to negative 2 dx. So getting its fraction form, so you have dx all over x squared. So notice that we have an dx over x squared in the given equation. This one here. Okay. So since it still has a negative sign, so divide by negative 1. So we have negative du is equal to dx all over x squared. So this term here is this one. Your e term is this one. Or 1 over x is this term here. Okay, so by replacing the values, so we have 6 integral of e raised to the power of u. Then your dx, your du is negative du. So we have negative 6, taking negative 1 outside the equation. Okay, so we now have e to the power of u du. So again, the answer for this one is negative 6. So multiplying your negative 6 to the answer, that's eu plus c. So bringing back the value of your u parameter, that's negative 6 e raised to 1 over x plus c. So this one is your final answer. Okay. So last and final example. So again, still your e to the power of u du is equal to eu plus c. So again, e is still e parameter. So e is still e. Then your u parameter is sine of x times cosine of x. So getting the derivative of your u parameter. So again, since we have two terms, we're going to have to use the chain rule or the product rule of your derivatives or your differentiation technique. So that's u dv, so sine x, then derivative of cosine, that's negative sine, plus v du. So plus cosine x, then derivative of sine is cosine. Okay, then dx. Okay, so you have negative sine squared x plus cosine squared x dx. So rearranging the formula so that your negative sign is on the second term. So you have cosine squared x minus sine squared x dx. So notice that so we have replaced e here. We have replaced sine x, cosine x with your u parameter. So the remaining term is cosine 2x dx. So looking at our derivative, so we have cosine squared x minus sine squared x. So how do we go about this? So this one is actually equivalent to this given term here, because if you recall your double angle identity, so this one is called double angle identity. Okay, so your cosine double angle, cosine 2 theta, is equivalent to cosine squared theta minus sine squared theta. And the other format for this one, is 2 cosine squared theta minus 1. Then the other format is 1 minus 2 sine squared theta. So this one is a double angle. So we can represent your du with cosine 2x dx. Okay, so this one is this term here. Okay, so we have e raised to u du. So the final answer is e raised to sine x cosine x plus c. Okay, so do you have questions? So no questions.